Alright, so let's start. We would like to prove this proposition using induction. So for n equals 1, this becomes what? dx1 x1 is less than or equal to dx1 okay, actually for n1 it doesn't make sense, right? Maybe I should start with n2. So in that case, distance from x1 to x2 is less than distance from x1 to x2. Well, of course, it is the case, right? Now assume the result for, let's say, n equals k. This means what? Okay, we assume the result for n equals k. Now let n equals k plus 1. So let x1, x2, xk plus 1 be some points. Then we have what? Then the distance from x1 to let's say k plus 1 will be what? Well, this will be less than distance from x1 to xk and xk to xk plus 1, right? This is just the triangle inequality for x1, xk and xk plus 1 by the triangle inequality for the triple x1, xk and xk plus 1. However, by assumption, by the induction assumption, on the other hand, by the induction hypothesis, we have what? We assume the result for n equals k. So we have this. The distance from x1 to xk is less than x1 to x2, x2 to x3, up to xn minus k, sorry, xk minus 1, xk, right? We assume this. And if I take this and plug here, right? I take this one and plug into the above equation, we get what? So dx1 to xk plus 1 will be less than what? Instead of this term, let me underline it. So this one, I will write something bigger. This one. So I will get an expression bigger than this. So instead of this one, I am writing dx1, dx2, dx2, dx3 up to dxk minus 1 xk. And finally, I have this term dxk, dxk plus 1. And this is what we wanted to prove, right? Hence, we are done. So, using just the tree hypothesis, we proved this interesting facts about metric spaces. Pictorially, this is something like this, right? I have n points: x1, x2, x3, x4, x5, whatever, xn minus 1, and let's say xn. This means what? The distance, again, this is not the real picture, this is just a symbolic picture, right? It tells us the following: this distance is less than or equal to the sum of the consecutive distances. So it is, you take this distance plus this one plus this one and so on, right? And finally this distance. So the red one is less than the sum of the blue ones. This is what this easy fact tells us. Although this triangle inequality is something very simple, we will see that it yields so amazing facts. Okay, so never underestimate the power of triangle inequality. It is something really important. Okay, do you have any questions so far? If you don't understand anything, just stop me, okay? Another fact, a simple fact, which we will make use of a lot, is the following. Uh, let xt be a metric space. Then for any points x, y, z, and w in x, so whenever you pick up 4 points, we have the following: distance from x to y minus uh, uh, sorry, okay, yeah, let me write it. X to w and y to z. And if you take the absolute value, these are real numbers, so I can take the absolute value. This distance is always less than dxy plus dwz. Okay, yeah. Again, this will be an easy consequence of triangle inequality. Let's see proof. Well, let's look at the distance. So we will use the following, the above proposition. I have 4 points, right? x1, x2, x3, x4, and I can write this. So by the previous proposition, we have this. Distance from x to w will be less than distance from x to y, y to z, and z to w, right? So, hence, taking this term to the left hand side, we get what? dxw minus, sorry, xy, yz, zw. No, I am taking this one to the right hand side. All right. Okay. Right. This is the, yeah. So this is less than what? I took this one to the left hand side. So we have dxy plus zw. All right. Okay. Now let's do the following. Let's replace. Uh, let's replace the letters uh, uh, x and y, x bit y, and uh, z with w. So this is not mathematics, right? In the alphabet, whenever I see x, I will write y. Whenever I see y, I will write x. And whenever I see z, I will write w. Whenever I see w, I will write z. So what happens to this inequality then? Then the above inequality becomes what? So instead of x, I am writing y. Instead of w, I am writing z. Instead of y, I am writing x. And instead of z, I am writing w. Here, instead of x, I write y. Instead of y, I write x. Instead of z, I write w. And instead of w, I write z. What happened? Well, you see, this expression is just the negative of this expression, right? Exactly the same, but with a minus sign in front. So I have minus, this is just minus dxw minus dyz. What the right hand side? Well, since distance function is symmetric, this is just exactly this expression. This is just xy plus zw, right? Exactly the same expression. Well, now let's look at what we have obtained. We obtained the following inequalities. Let me uh, write them down. I have this inequality and this inequality. And you see, whatever this number is, it is less than this number, and the negative of that number is also less than the same number. Hence, right? If you have a number which is less than something else, and if the negative of that number is also less than that number, then the absolute value of this number should be less than this. Why is that? Hence, what is the absolute value of this real number? dxw minus dyz. Well, I don't know what is the absolute value, but it is either this number, right? Because absolute value is either uh, the number itself or it's negative. So it is either this one or this one. But in both cases, it is less than this number. Therefore, the absolute value is less than this. And this finishes the proof. Okay? Do you have any questions so far? Okay. All right. a remark about this. So if you let, for example, y to z, y to z, uh, if y equals z, no, okay. This will give us the triangle equality. I had something else in my mind, but I cannot remember it the right way. Okay, let's now talk about some examples. I will spend the rest of the lecture on examples. The first one is x is the set of real numbers and d is the absolute value function. How? So d is this function. dxy is just the absolute value of x minus y. We have already seen, actually, this satisfies the triangle inequality, but let me go over it one by one. So we claim that this is a metric space, so I have to prove that this satisfies three you know hypotheses about matrix m1. M1 was what? So it is dxy, x minus y. This should be always non-negative. Well, it is the absolute value of a real number, and we know that this is never negative for any xy. And dxy, uh, dxx is 0, right? Or maybe I should write dxy is 0 if and only if and only if, right? X minus y in absolute value is 0, but this is possible only if x equals y, right? Otherwise, that expression is never 0. So this function satisfies the first hypothesis for metric function. The second one, it has to be symmetric. Well, what is dxy? This is the absolute value of x minus y. Of course, this is the same thing as the absolute value of y minus x, but this is just the distance from y to x. So D satisfies the second metric property. Let me put a check here. And the third one, the triangular inequality. Well, let's see. Distance from x to y. Well, this is just this by definition. I can write the following. I subtract and add z, and I can apply triangle inequality to the sum here. Right? I have absolute value of a plus b. We know that this is less than a plus b, but you see, we have then this is less than distance from x to z plus distance from z to y. And this is true for all x, y, z in R. So hence the set of real numbers uh, together with the absolute value metric is a metric space. Okay, I will call this as the absolute value matrix dxy equals absolute value of x minus y. This really, right, whenever you have two real numbers, it just gives us the distance between these two, right, real numbers. All right, let's see. Okay. What else? I have maybe something you are more familiar with. Let me choose x to be R2, okay, the usual plane, and d to be the following. So uh, uh, let's say the following function R2 from R2 into R defined by. So I will just give you a pair of points in the plane. The first pair, let's say x1, x2. The second pair is y1, y2. What will be the distance? This will be just the usual distance, okay, in the plane. So difference of the first coordinates y1 minus x1 squared plus difference of the second coordinates y2 minus x2 squared. This is a bit confusing because, so here our plane is like this. So this is, let's say, the first axis. This is the second axis. So this is x1, x2. I have another point, y1, y2. And this is really the distance, Euclidean distance between these 2 points, okay? Uh, More generally, we can define the following. More generally, let x to be Rn and set d from Rn cross Rn into R uh, given like this. So d, okay, let me maybe I write here. D, let's say x1 up to xn, y1 up to yn. So I have 2 n tuples. Each represents a point in Rn, and this distance is defined to be the following expression, the Euclidean distance between these 2 points. So it is just the square root of the difference of the first coordinates. So y1 minus x1 squared, and then y2 minus x2 squared, and yn minus xn squared. Okay, square root of this expression. And we claim that this is a metric. So claim D is a metric on Rn. So we have to prove that D satisfies M1, M2, M3. All right, so let's see. what is M1? M1 was the positivity condition. Well, you see, this expression, okay, let's say PQ, let's say P is one of them, Q is the other one. This is the square root of a non-negative expression. This is never negative. It is at least 0. And square root of a non-negative number is never negative. So this is always positive for all PQ in Rn. And if P equals Q, then of course P is this point, Q is this point, then xi is equal to yi for all I from 1 up to n. But then, of course, these are all 0, hence, thus, dpq is just, right, 0 squared, 0 squared, and so on, which is 0. And if this is 0, moreover, if dpq is 0, so if this is 0, maybe I should write like this. yi minus xi squared I from 1 up to n, and then I take square root, right? So if this is 0, then of course the expression inside the square root is 0, then this is 0. But all of these are non-negative numbers because they are squares of something. And this sum is 0 only if each one is 0, right? Because none of them is negative. They are all non-negative and the sum is 0, which implies xi minus yi squared is 0 for all I from 1 up to n. Hence, right, this means the absolute value of yi minus xi is 0, but absolute value is 0 only if the term inside is 0. Therefore, yi is equal to xi for all I, but this means so that P equals Q, right? Maybe I write like this. P is this one, Q is this one. The second, do you have any questions so far? Efendim? Tamam. Böyle iyi mi? Tamam. The second property is the symmetry property, right? So dxy equals dpq equals d y. Okay. So dpq. What is this? This is the sum I from 1 up to n xi minus yi squared and square root. But clearly this is just I from 1 up to n yi minus xi squared square root, and this is of course dqp. So the second property is clearly satisfied. For the third one, we need Cauchy-Schwarz inequality, right? To prove, okay, so the PQ should be less than dPr plus dRQ, right? For all PQR in Rn. For this, we need Cauchy-Schwarz inequality. Schwarz'ı yanlış yazdım. Schwarz inequality. What is the Cauchy-Schwarz inequality? It is the following. We know that Rn is a metric space, right? Rn is a metric space. Sorry, inner product space from linear algebra or advanced calculus inner product space. For any vector or two vectors, now I will consider these as vectors. Yn, right? The inner product PQ is defined to be sum of the products of the components, right? I from 1 up to n. And what is the Cauchy-Schwarz inequality? Cauchy-Schwarz inequality was this. The inner product of two elements in absolute value, so inner product of PQ, absolute value of this, is always less than norm of P times norm of Q. Of course, what is norm? Norm is just where norm of P is just the square root of the inner product of a vector with itself, right? So this means what? This means the following. Absolute value of xi, yi, I from 1 up to n. This absolute value is always less than norm of P. So norm of inner product of x with itself. So that is just sum of squares of the term components of the vector P. And this is the Cauchy-Schwarz inequality, right? This is the Cauchy-Schwarz inequality. I guess you remember this from both linear algebra and advanced calculus, or maybe even calculus, I don't know. Okay. Now, how can we prove the M3 property now? What was M3? So we'll let P to be x1, xn, Q to be y1, yn, and R to be z1, zn. Okay. All right. So we have to prove that distance from P to Q is all right. Okay. So distance from P to Q, P to R, let's say. So what is this? This is just distance. Okay, this is just what is this? This is the all right. The length of this vector, right? The length of this vector. Yeah, maybe. Okay. All right. So, right, because this is by definition xi minus zi squared, sum of all of them, and then square root. This is, of course, the norm of the vector, okay? And we would like to prove the following. dpr this will be less than the sum of the other two differences. We can do the following. Put q here plus q here, and then apply triangle inequality, right? Which is just the tq plus qr. So you may wonder, why did we stated Cauchy-Schwarz? Cauchy-Schwarz gives us the triangle inequality, this one, right? Cauchy-Schwarz gives us this one. How? So here, Cauchy-Schwarz is used to prove the triangle inequality as follows. Bunu lineer cebirden belki hatırlıyorsunuz. Maybe you remember this from linear algebra. How? So let me do it this way. Let V and let's say W or U and V are two vectors. Then norm of this vector, right? What is this? This is just U plus V norm squared inner product. Let me write inner product like this, U plus V. Inner product can be distributed as follows: U dot U and then U dot V plus V dot U plus V dot V. So this is norm U squared, and then I have norm V squared, and then I have 2 times U dot V. Now here we use the Cauchy-Schwarz, right? Instead of this inner product, I can write this. Sorry. The inner product of u and v, the absolute value of this is less than norm of u times norm of v, right? This is exactly the Cauchy-Schwarz. Inner product of two vectors in absolute value is less than the product of the norms of these vectors. So we use that one here. But this expression is something, familiar. This is just norm u plus norm v squared, right? Now I have square of this expression less than or equal to square of this expression, and thus we obtain the triangle inequality by just taking the square root of both sides. We obtain this. So we use the Cauchy-Schwarz to prove the triangle inequality for the inner product space, and we use that one to prove the triangle inequality for the metric space. Okay, so hence Rn with this metric D is a metric space. Actually, I will call this metric D2 metric is a metric space where D2 is this one. D2. So PQ, P is x1 to xn and so on. So it is this one. I from 1 to n xi minus yi squared and then square root. Where does this 2 comes from? Come from? It comes from this expression. It is the 2 here, okay? I have 2 here and 2 here. This, of course, suggests a generalization, right? Generalization. So this is a metric space. We can define similarly. We may define D1 and D1, let's say R, or not R but rho, and D infinity as follows. D1 şu, D1 is the metric. So these are all metrics on Rn. They are different metrics, okay? D1 is this one. So D1 PQ. Similar to this one, instead of 2, I have 1. So I will not take square. I will just write 1 here, first power, just the absolute value. And to the power 1 over 1, which is 1. So D1 is just this. I from 1 to n xi minus yi. This summation, right? To the first power and then to the first root. D2 is that expression. What about D rho PQ? This will be just root power and then 1 over rho. Here we will assume that rho is at least 1. It can be 1, but uh, it will be always larger than or equal to 1. And D infinity, so these are definitions. D1 metric is this, D rho metric will be this, and D infinity metric will be the following. As this notation suggests, we will just take the limit of this rho as rho goes to infinity. As rho goes to infinity, what happens? You see, you take root powers. Suppose you have 3 numbers and you are taking powers of this. Whichever is the bigger, let's say for example you have 2, 5 and 10. When you take powers of this becomes 5, 25 and 100. And then 8, 125, and this becomes what? 1000, right? This will be 16 and this will be 10,000. You see, the bigger one will dominate the rest. Okay, uh, and this is the idea here. The bigger one will dominate the rest, and when you take that thing outside this 1 over root, that will survive. Rho will cancel with 1 over rho, but the other ones will disappear, right? They will go to 0. So this will be just the surviving term of this as rho goes to infinity. In other words, it is just the maximum of this expression, maximum of x1 minus y1, x2 minus y2, xn minus yn minus. Okay. So if you let rho go to infinity, this expression will give you the maximum of this. Okay. It is easy to prove D1 and D infinity are metrics, but for the rho, we will need analogues of Cauchy-Schwarz and triangular inequality for this kind of expressions. And it is not that easy. I'll do it later, but next time we will show that. I will start by proving that D1 and D infinity are metrics, okay, like D2. As I said, they are all metrics, but proving that this D rho is a metric is not that easy. We need some analogues of Cauchy-Schwarz and triangular inequality for this kind of expressions. Okay, and I will also talk about the discrete metric next time. I guess we may stop here for today. Next time I'll continue.